converting data across data types. Now here first, I need to remind ourselves what do we mean by data types or measurement types, or in the textbook, they use this terminology of scale types. And the way I think they do it is that they call scale types both measurement types and data types, but I like to distinguish these two. So measurement types is more on the mathematical conceptual side, okay? This is mathematical conceptual statistical side of things. The data types are for the programming configuration. And sometimes they match, but it's not one-to-one, it's not directly. So usually nominal or categorical variables are depicted as character or text data, right? So Chinese food, Italian food, hamburgers, and so on. These are all kind of character or text. Ordinal can be character or text, such as poor, medium, or good, right? Poor, medium, or good has an order. Ordinal has to do with order, but also these can be shown in integer, 0, 1, 2, or 1, 2, 3. So integer can represent ordinal values. Interval can be represented with integer values. Interval has no true zero. Can be represented with float values, or it can be represented with date. So interval can be represented with these three different data types of the computer. And ratio, which has a true zero, it's a number and has a true zero, is usually just integer or float in decimal. And I have a nicer chart over here in different colors, so you can take a look. So these are a little, they are distinguished for sure. But the textbook calls, I think, all of these kind of scale types, although I think scale types is something other that we'll talk about in a second. So notice also, I forgot here the binary data type, but that's just, but I added here, any measurement type can be represented in binary data types. That is, any category, nominal or categorical measurements, ordinal, interval, ratio, they can all be represented in binary, which is 1 or 0, or true or false, or 1 or 0. So I'm not, maybe interval and ratio could not really be binary, but so that's kind of like maybe gets a little bit too deep, but almost pretty much, I think any measurement type can be binary, including we can convert categorical data to binary data as well in terms of 0 or 1, and I show you how. So suppose we have original data. This original data is over here on the left side. So we have all this data about food and age of the people that ate the food, and distance from the restaurant, and then company, whether it was a good company or a bad company. So these here are categorical values: Chinese, Italian burgers, Chinese burgers, the kind of food they're talking about. So how do you turn this into binary or numeric binary data? Well, you just create one variable for each of the existing values. So if there's 3 kinds of foods, Chinese, Italian, or burgers, then you have 3 additional variables. And if the particular row is that food, then you get a 1. So, right, so here, food 1 means burgers. This is burgers. Food 2 means Italian. And food 3 means Chinese. So the first one is Chinese, so it's not burgers, 0. It's not Italian, 0, but F3 Chinese is 1. Now, of course, the issue is, suppose you have 100 different kinds of foods. So that's one variable with 100 different values. But if you translate that into binary, then you have 100 new variables. And then the zero counts as a value. The 0 is nothing. It's not empty. It's just actual value. It means 0. So that adds a lot of dimensions. That's a lot of features, dimensions, and it adds a lot of content to our data, which can make things more difficult. But of course, once we turn it into binary, this is a number format, 0 and 1. It has a 0, which is a kind of a true zero means that we don't have that thing, or a one that we do. So we can make all kinds of numerical calculations on it, which can be very useful. Also, there's the notion of converting to a different scale. And in the textbook, they do call it different scale. And I think of this way more of a different scale. So kind of like going from kilograms to pounds. Or there's some other examples here, Euclidean distance. We don't need to go there. But this one's kind of interesting. So for example, normalization using minimum max rescaling. So maybe you have a data, you have 3 records or more, 3 or 300, and you have education information. And the lowest education is 2, and the highest education is 4.2 years. The lowest education is 2. So maybe you can kind of normalize that data into the lowest value. The minimum is going to be 0, and the maximum is going to be 1, and everything else kind of in between. And that's a way to normalize or standardize the data based on a particular measure, in this case, minimum and maximum values. Normalizing using other kinds of standardizations is possible as well. And we kind of did some of that, right? So even when we're doing, we have taxes information. Well, total taxes for a state, it's hard to compare across states. So we divide total taxes by population, and we create a normalized measure of taxes per person. And then it makes it easier to compare from state to state that may have different populations. Data transformation. So other types of data transformations may be necessary to simplify the analysis, improve predictive power of the models, or to enable use of particular modeling techniques. So all these kind of conversions are kind of data transformations that we just talked about. Maybe they're measurement transformations or data type transformations or scale transformations. But some of the other ones that are often used are applying a logarithmic function to the values of the relevant attributes or variables that we're talking about. And this is usually performed for skewed distributions. So when some of the values are much larger or much smaller than the others, for maybe 2 variables that you're comparing, and the logarithm makes the distribution less skewed. So log transformations can give us better interpretation of highly skewed data. Also, other things we can do is convert to absolute values, pretty straightforward. So if you're only interested in the value's magnitude, so it doesn't matter if it's negative or positive, you just want to see the difference between some kind of center point, then you can just take the absolute value of all the numbers. And that can be useful too. But let's take a look at the logarithm example. So suppose you're comparing salary and dinner expense. You want to see if there's a correlation between how much people spend on their dinners and the salaries that they have. The thing is, salaries range from 17,000 to 1 million. So that's a big difference, right? That's a difference of more than 980,000. Now, dinner expenses only go from 2,000 to 120,000. So that's only a difference between of 118,000 about. So if you look at the original graph, you would look something like this. Everything is kind of concentrated here on the left and some big outliers on the right. So this is income on the x-axis and dinner on the y-axis, because these scales are just too distinct. Now, if you apply a log transformation, log 10, any kind of log, you can kind of extend that a little bit so it's easier to visualize and sometimes also better to calculate as well. So you take the log of income and the log of money spent on dinners, and you stretch out that skewedness and better see the relationship between variables. And next, we're going to be talking about dimensionality reduction.